In this video, we are going to look at dynamic memory allocation. I think the best way to start with this is kind of look at how memory works with us most of the time, which we've done a few times, and then expand how this works with dynamic memory allocation. So yeah, I have some simple code here. These first two lines should be pretty, you should be pretty comfortable with, but let's talk about what happens when we run these things in memory. So remember that every time we run a function, we create a memory space called the stack frame, and we allocate memory needed for that function. When a function is done running, the stack frame gets deleted. So every time we create a variable, we put an entry in the stack frame. And these two lines of code right here would basically look something like this, where we have our X variable and our array elements all stored in the stack. Now we know the word AR here is really a pointer to the first element of this memory. But this is how everything works that we've looked at so far. But what happens when main calls this function here? Let's go take a look at that function. You'll see in this function here, we enter this function. We're going to create a stack frame. It's going to make some space for an array, some space for this pointer, and it's going to try to return the pointer. Of course, when this function finishes writing, this stack frame will be deleted. And this is going to cause us a problem. If we go look back up at the code at the top, we are returned a pointer from this function call. That gets assigned a new array, and then we try to access new array, and this is a problem. This is not guaranteed to actually work. I'm going to bring up a website I've referenced a few times so we can kind of see this in action. It's called Python Tutor, but this is the C Tutor, Visualize C, and it allows you to visualize code in memory. So we have our same code here, create some variables, have this call to a function that returns a pointer, and I have the function down here. We don't actually need all of this here. We could just return array, but I want to be very explicit that there's a pointer to an array that we're returning. So let's visualize this. Let's see how this works. The drawings are just neater than my drawings, same information. So we have our stack right here. This is main's stack frame. We can see that we've created an X, we've created an array, and we have a pointer, and we have this Z variable, none of which has actually done anything yet. We haven't run any of this code yet. We're just allocating the memory. So let's walk through. We'll see we initialize our data, and then we get to this new array to this function call. So we obviously can't assign a value to new array until the function works. So when we enter the function, we're going to create a new stack frame. Here's our new stack frame. It has this array of 1, 2, 3. It has this pointer that points to the array. Now we're going to return this array to our main, and that will work. I mean, it will certainly return the pointer. So what will exist here is a pointer to this. But we have this problem, is that as soon as this function runs, this memory here is going to be deleted. So what are we pointing to? So let's take those steps. So we're going to return the array right now, and we return it, and you can see in our new array, they use the poop emoji, which is just means garbage. It means nothing, and there's nothing. This is pointing to nothing because the thing it was pointing to no longer exists. And then we can try to reference this as Z equals new array 0, but the problem is that new array doesn't actually point to anything. So we're going to get an error, and it's going to fail. So typically this would be called a segmentation fault. It's accessing a pointer that doesn't point to any allocated memory. There is the chance that that memory that we made still does exist, and there are some times where you'll be allowed to kind of access that, but you can consider that sort of inconsistent behavior. So you can't count on that happening. You really have to deal with it in other ways. So this will not work. This will not work. If you want to create an array inside of a function, you can't do it this way. And that's because the memory that you created in doesn't exist anymore. It's gone with the stack frame. So what we need is another place to store memory. And it's actually in this picture right now, it's the heap. And so the heap is another memory location that allows us to persist beyond stacks. So let's take a look at what I mean by that, and then we'll run some more code. So let's look at this other function called build array right here, build array. And this, which we're going to look at in a second, it does something called a malloc, which means it allocates memory. And we're going to talk about how that actually works in a second. So we've got a pointer to some allocated memory. We assign the, typo, well, that's a copy and paste error, 1, 0, 1, 2. And we assign the values 1, 2, 3 to the elements and then return the pointer. And this will work. Let's run it in our code. And I'll copy and paste it. All right, so we've just changed this one line with one function call where we build the array. So this one should work. Let's copy this code, bring it over to CTutor. I'll get rid of the commented code just so it's easier to read. All right, so here we go. Will this work? Visualize execution. Oh, missing semicolon. Not sure how that happened. Getting there. There it goes. All right, so same beginning as before, nothing different, stack frame with all this data in it. The question is, what happens when we build array? Well, notice we haven't allocated the memory yet for that array, unlike the last one where we have that memory allocated. We do have a pointer. This malloc means allocate memory in the heap, and I'm going to go into the details of how it works and what these parameters mean and stuff. So there it is, boom, we just created this array in the heap and we have a pointer to this array. We can assign those values. And then when we return the pointer to main, notice that our array in the heap is not in the stack frame. So when the stack frame gets deleted, the array in the heap will still exist. And we can see when our return, we now have a pointer to this array, and we can do the other tasks here in the code. So that's kind of our motivation here, persistent memory beyond stack frames. We can get into the details of how this works. There is something that I should note here. When you allocate memory, it is also your job to free memory, which I have not done yet, but we will also do that. So when you create memory, you must also delete memory. Otherwise, you end up with something called a memory leak. Maybe you've heard of that. It's basically when you just allocate memory and don't remove it and eventually run out of space to allocate more memory. I like to think of it as a restaurant with dirty tables. If no one ever busses the tables and you just keep on getting dirty tables and no one ever cleans them up, eventually you run out of tables to seat new customers. So if you use a table, you need to clean up that table, and then you can allow someone else to sit there. If you allocate memory, you clean up that memory to allow other parts of the program to allocate more memory. All right, so let's go back to our main code here. So that was kind of our motivation, but let's get to like actually what is going on. What is the story here? What's really happening? And we'll start with these 2 lines of code right here. Something a little weird here, void pointer. We've never seen that before, I don't think. Void pointer just means no data type. just a pointer to memory. So we're not specifying whether these are integers or doubles or floats. We're just saying pointer to memory. And this is a terrible thing to do. I don't recommend you create void pointers, but I want to give you some sense of how this stuff works. So we have this void pointer to heap, and I'm going to call this function malloc with a number. Now malloc requires the number of bytes you want to allocate. So I want to allocate 40 bytes. If these are integers, that's 10. If they're characters, there's 40 of them. If there's floats, there's 10 of them, right? It's just however big the array, however much memory I want to make. And you can think of this as an array, but it doesn't have to be an array. It's just memory. C doesn't imply any kind of context on it when you just have malloc. We'll talk a little bit more about how you can change that. So we have this pointer, and now we just create a malloc of 40 bytes in the heap, and then assign that pointer to the memory that was allocated. This is a terrible idea because it doesn't have any data type and it doesn't really tell you how this will work. So a much more common way to do something is to instead have something like, say, a pointer to a double, and then you can cast your allocation. Now in this case, I'm actually just gonna point it to the same memory because I wanna show you something. And you can see I can actually do that with all of these. I can say that memory is an integer, a collection of integers. That memory is a collection of doubles. That memory is a collection of chars. The pointer is like a view on the memory. So whatever data type the pointer is, that's what kind of like glasses I'm looking at the memory with. So if I have a pointer, a double pointer, then I'm looking at it like it's a double. If I have an int pointer, then I'm looking at it like it's an int. If I have a char pointer, then I'm looking at it like it's a char. And you can see I've casted each one of these to the corresponding pointer type. And that just stops it from being a void type. It really is void type when it returns. This returns void star as its data type. That's the return type of malloc. That's the prototype for malloc. Return a void star, call malloc, give it an int. So we can actually view this a bunch of different ways. And if I run this code in CTutor, if I run this code in CTutor, so we don't have any errors, and the CTutor doesn't support everything, just to be clear. CC is unsupported features. We may run into some things that CTutor doesn't allow us to do. So we're going to make a void pointer, which is weird, but you can just see there's 40 elements just hanging out here. And you see void byte, void byte, void byte, meaning it doesn't know what data type it is. And again, you really don't want to do that. I'm just trying to give you like the nitty gritty of what happens underneath. Much more likely is you're going to use some data type. And so what we'll see here, though, what I want to show you is, I don't know what I did there. Is that all those pointers are pointing to the same piece of memory. But when I look at char, the pointer underscore s, it looks at this like a string. If I look at pointer underscore I, it looks like an array of ints. If I look at it with pointer d, then it looks at it as a pointer to doubles. And it just matters what I make the data type here. That's all it is. Just whatever the data type is what makes this the data type that it is. You can also leave off the cast and just leave it off entirely. Just don't have the cast. Just say int star ptr underscore I equals ptr to heap. That would also work. It's probably best to use the cast, but that would also function. So this is kind of the idea. We can allocate memory of any size we want, and we can apply data type to that memory whenever we want. This is all very contrived. This is not typically how we would use any of this. Typically, how we would use it would be something more like these. Say we want to ask the user how big of a list they want to store, and they tell us they want to store 10 elements. And let me just actually put that in here. ask the user to enter a number, and then make some variable for them to store it in. Now you want to make an array of that size, and some compilers in C will let you use a variable in your array brackets, but not all of them. It's considered non-standard. So the way we handle that is we use malloc. So we create a pointer of an int array or an int star, which again is just an array or anything else we want it to be. So a pointer to some memory. Think of it like an array, and it's in the heap instead of in the stack. Right now it doesn't exist. Excuse me. Right now it's just a pointer to nothing. So we need to allocate some memory and assign it to that pointer. So you can see here, we're going to allocate some memory, malloc, but instead of putting a single number in, I'm actually doing a multiplication. Well, what's my multiplication? I want n number of ints. So I have to multiply the size of an int, however big an int is, times n, that's how many spaces I want. So I want n ints, and that's going to allocate the amount of memory that I get. So it's just a little multiplication problem. Give me size of int, and then do that 10 times. You could say double, you could say jar, you could say any data type that you want, structs, all kinds of stuff. Size of whatever that thing is, I want this many of them. So give me malloc, size of int, and multiply it by n. So if int is 4 bytes and n is 10, you'll get 40 bytes, which is 10 elements, 10 arrays, 10 array elements. And then we assign that to the pointer. Once we have that, we actually can use this as an array. Now, be forewarned, this array is full of garbage with malloc. Malloc does not initialize any data. It only allocates memory. So we can be assured that whatever we have in here is just garbage. Let me just print out all the garbage so we can see it. And int. So you can see we can just use it like an array, and I'm just going to print out all the garbage, and we should see it print out a bunch of garbage. Let's run this. Oh, error. I'm missing in semicolon. Oh, right here. And we'll run it. And we should get prompted for a number. I'll say 5. And there is our 5 values. Now these just happen to be 0, but you can't guarantee they're 0. It's going to be garbage. It's just that this happens to be 0. We could also, though, assign values here if we wanted to. We could just use this like an array. Can't guarantee what's going to be in garbage, but can guarantee that will be garbage. In fact, we should. Maybe we can run it in Python tutor, and it will show us garbage. C tutor, Python tutor, same thing. Let's see. All right, so we have this n. We're going to ask the user for how many. I'm going to enter a number and enter it somewhere. No, it didn't give me a place to enter it. Let's try that again. I think I'm supposed to enter it in the little top part. That's the output. I said this is sometimes come with limitations, so we might not be able to do this here. Enter a number. I can't type in here. Well, that's not going to work unless it lets me change what that number is. Yeah. All right, well, we won't be able to do it here. Well, again, this is just full of garbage. You can't guarantee it. Now, there is like a cousin of malloc called calloc. And the difference between malloc and calloc is pretty simple. The parameters are a bit different, but more importantly, it just gets initialized. So I have this other pointer called zeroed out, and then I'm going to calloc, and it's the same pieces of information, like how many size, how big of a thing do you want, and how many things of that do you want? It's the same information. I want 10 elements of size int, and I'm going to calloc that. Calloc, the C stands for clear allocation, and the M in malloc, it stands for memory allocation. So just allocate memory versus clearing memory allocation. In computers, the word clear generally means to set to 0. The word set means to set it to 1. So clear just means 0 it out. So clear allocation means 0 everything out. You're guaranteed to have zeros here. And if I were to run this as well, we should get some more zeros. This time, though, I can guarantee they're going to be zeros and not just luck that they're going to be zeros. And yeah, we printed all the zeros out. I don't have any new lines in there. So 6 of them are the first thing. All right, so that's malloc and calloc. That's really the mechanics of them and like the theory of them. But I want to talk a little bit about how we could use this stuff. So why would I care about this? Well, one is, as I said already, and we can go back and look at this function, is that you care about this because it allows you to create memory in the heap, which then can be returned from a function. So here's our malloc, just going back over our malloc in this array, build array. We malloc 3 elements of size int. A lot of these examples are of size int, but they do not have to be. They can be anything, any data type. All right. What's another good use for this? Well, another good use for dynamic memory allocation is allocating arrays and strings when you don't know how big they are to start. So imagine I wrote some code that asked a person to enter their first name and asked a person to enter their last name. I want to concatenate those 2 strings to one string. So I just want to say Michael Penta as one string. The problem is I don't know how big string cat works, but by inserting the second string into the first string, if you remember from last week. And the first string has to have enough space to fit the second string. So if I don't have enough space to fit the second string, what do I do? So, so here is an example of allocation using strings. So I'm gonna break this down just a little bit. What I need to figure out is what's the size of the final array. What's the size of the concat string? How many elements do I need? Well, I'm going to need all of the elements from the first word. So I'm going to have to get the string length of first name. You can see I have first name and last name right here, first and last. And then, of course, I need that plus the string length for the last. And if I want to make a string, I need a null terminator at the end. So I better add at least one more. If I wanted to concatenate a space between them, I better add 2 more spaces. And so that's my size. My size is the size of the first string plus the size of the last string plus 1 for the null terminator. And I can allocate that memory I can malloc that much stuff. I should cast this to a char star. Again, it's not required, but it's better. And so I'm saying, go get me some memory that's as big as these 2 strings plus 1 more, and then assign that pointer full name to that memory. Now that memory is just exists. It doesn't have anything in it. It's just a piece of memory, right? It doesn't have anything in it yet. So the first thing I want to do is I want to copy the first name into that. So I'm going to take a copy of first name and I'm going to copy it into this full name. Now full name has way more room. It has enough room to fit much more stuff. So we're going to then concatenate last name to full name, and that's that's going to give us enough room here with the new line and with the null terminator and everything. Because remember, the first string's null terminator is replaced by the second string, and then the second string null terminator is left on to make this a string. So that's a string cat. And then here I just print out the name so we can see it print. Let's give that a shot. And there's my malloc, and I just created some arrays. And you can see it printed out Michael Penta. If I wanted to allocate, enough room to put a space between them, I need an extra byte for the character, and then I'd have to do one more string cat here. I'd have to do a str cat of full name and the string of an empty space. And that should still give me enough room for my space. So allocate memory on the fly based on things, on data you have. The difference again between calloc and malloc is that they are zeroed out or not zeroed out. Let's take a look at this one in Python CTutor just to see if we can check it out. Ooh. All right, waiting. All right, here we go. We are going to allocate some memory for our first element, our second, and now we are going to create a size concat of 14. Well, 7 plus 5 plus 2 more for the space and the null character, that is 14. And then you can see we allocate enough memory for all 14 characters. We copy the first name in, we copy the space in, we copy the last name in, and then we can print. You are gonna probably run into some errors called segmentation faults. Segmentation faults are when you do not have memory allocated. Let's see if I can force one. And there we go, segmentation fault. Every time you see a segmentation fault, that means you have not allocated memory somewhere. So you're accessing memory that has not been allocated. So for example, here, without this malloc, this char full name is just a pointer to nothing. It's just a pointer to nothing. And then when I try to copy first name into that, there's nothing there to copy. And that is a segmentation fault. So if you have not allocated memory by some means, then you're going to get a segmentation fault if you try to access it. I think that's about it. Remember, strings are just pointers, arrays are just pointers. The big difference here is we're going to create pointers that we can allocate on the heap instead of on the stack, which is going to allow us more power over memory, allow us to pass and return things. Allow us to return things that we create in arrays out of arrays, allow us to dynamically allocate memory on the fly based on calculations we're doing in our code, like this right here. So I think that's it. This is can be a little bit of a challenging topic. Just takes a little practice though.